Hi, my name is Celeste Fralick. I'm the Chief Data Scientist and Senior Principal Engineer in the Office of the CTO at McAfee, a cybersecurity company. Today I will be speaking about AI reliability, but first I'd like to baseline everybody with the analytics pipeline. Back in 1940, predictive analytics emerged, followed by AI being proposed by John McAfee in 1956. Neural networks emerged by Frank Rosenblatt, only to be dismissed 11 years later. And fast forward to 2001, where Dr. Tom Davenport reported in Harvard Business Review that data scientist job title was was very sexy. And big data emerged between 1998 and 2005. IBM made Watson to make AI interesting again with Chess and Jeopardy. And finally, neural networks were acceptable in 2015, about the same time that Moore's Law was really super taking off. Moore's Law indicates that the density of transistors will double every 18 months. And without Moore's Law, we would not be able to perform neural networks or machine learning in 2016, which solved everything. And finally, marketing has placed all analytics under the term AI in 2018, and that's where it stands today. But in recognition of marketing's contribution, I will utilize the term AI throughout my story today. And the story today has shifted from model development to end-to-end usage, consumption, and management of those models. But things are getting a tad confusing with a lot of the terminology. So I'd like to introduce you to three terms that I'm sure you've heard floating around about AI. The first one is robustness. While the term can mean many things, typically it is referred to the ability of a computer system to cope with errors during execution and cope with erroneous input. We can extend that concept into AI. How effective is your algorithm while being tested on a new, independent, but similar data set? This property is also known as algorithmic stability. In many cases, we can use error rates such as low mean squared error or minimize noise to reflect AI robustness, such as using the peak signal to noise ratio value. And the next term I'd like to review is resilience. And through good and bad inputs and other challenges, you need to ask yourself whether the model performs the same way. Does a model have the capacity to recover quickly from difficulties? Resilience also implies toughness, ability to adapt to risks, and continued operation of core business functions despite disruption and stress factors. I have to ask you, are your AI models resilient? How would you know? The third term I want to introduce you to is trustworthiness. And I'm sure you've heard it. It's such a great word. It's the Boy Scouts use it. The National Institute of Standards and Technology in the US has used it. And ISO has, both NIST and ISO have developed AI standards that embrace this term of trustworthiness. Other governments throughout the world have also created summary and strategy reports, including trustworthiness, but have also thrown in the terms resilience and robustness for good measure. Now, while these three terms are used throughout AI, it's important to understand that they overlap in meaning, which is great for inclusiveness, but it's difficult to figure out the end game of why they're important. And to answer the why, as well as what is the goal of these terms, which isn't fully addressed in the documents, I'm bringing an old term back to our relatively new AI ecosystem. That is reliability. It measures the intended performance over time. It answers questions like, how long will my model last when applied to real data? How stable is my model? Can it adapt to risks? Can the user adopt AI without fear of privacy concerns? Incorrect conclusions that impact decisions are done by AI, and it can affect my work and my life. Well, being able to predict a model's reliability can assist in resourcing staff, dollars, training. It also eliminates potential customer escalations and reduce risk for your company. Robustness, or algorithmic stability, resilience, ability to adapt to risks, and trustworthiness, the ability to adopt AI without fear, are critical for determining a model's intended performance over time. Now, reliability mathematics have been around for a long time. They are applied to everything from our cars, our refrigerators, our computer chips and phones, to the very clothes we wear. It is the manufacturer's prediction, promise really, of how long the product will perform its intended function. It's the best buy date of your milk in the refrigerator to the recommended cleaning frequency of your teeth prescribed by your dentist. It is graphically shown here as a bathtub curve, with the first part of the tub reflecting initial quality and any infant mortality with a decreasing failure rate. And this reflects the lemon of a car you might have bought. As soon as it got off the lot, it didn't work quite as nice. This is the happy place down in the normal life or the useful life where you have a low or constant failure rate. And finally, at the other end of the bathtub curve, you have an end of life wear out or increasing failure rate. Now, this would be where you would throw out your milk, or your dentist complains that you haven't had cleaning lately. So do AI models behave the same way? Well, why would we care? We care because we want to create value for the company and the customer. We want to create something that lasts and something we can be proud of, something that doesn't die in the field the minute it goes live. And even though AI and machine learning models have that automatic retraining associated with them, provided you programmed it to, there comes a time in the life of a model that they are no longer suitable for the data or the system that they were originally trained on. Now, software reliability has also evolved over the years to provide an estimate of the level of business risk and the likelihood of potential application failures and defects that the application will experience when placed in operation. It is even utilizing neural nets and other AI tools to assess and predict failures. Software reliability still addresses core items such as errors detected at each stage, as well as functional and structural quality, typically sitting in an SQA organization. And we also use combinatorial test design to identify the optimum number of tests for the coverage that we desire. Now, Microsoft over here on the right, this paper speaks to reliability at Microsoft and refers to the Office Customer Experience Improvement Program, CEIP, and Microsoft Reliability Analysis Service, MRAS. And you can find details of these programs in this paper if you'd like to look it up. Now, the Consortium for Information and Software Quality speaks of reliability with familiar words we've already reviewed, like resiliency and stability, another term for robustness. They do mention monitoring, which is a critical concept for reliability. However, software has yet to address the reliability of an AI model in the field. Now, AI reliability doesn't fit squarely in general reliability models, nor software reliability models. A new paradigm needs to be considered so we can predict the life of a model in the field. Consider then these questions about reliability and AI. How do you utilize robustness, resilience, and trustworthiness? What are the specific factors that drive reliability? How do you predict reliability of an AI model? And how does AI reliability change over time? To give some guidance to answering these questions, we must look at the entirety of AI development and deployment in the field, from soup to nuts. Now, most developers are anxious to create the latest exciting model. As developers, DevOps, or development operations, has been a mainstay of developing code, as well as end-state models, for years. But DevOps is necessary but not sufficient. AI is more than just code. It is based on curated data that requires targeted actions built in from the beginning of and during model development, but also monitored once the model is deployed in the field with your customers. As an example, the top portion of this cartoon reflects a typical DevOps portion of model development. We want to design in transparency, explainability, consistency, multiplicative edge cases, and make our model efficient and less vulnerable, especially to threats, attacks, and bias. But we also need ML ops, complementing development and DevOps. It moves our development-centric focus to consumption-centric activities. And it is thought to increase our company's profit margin by 3 to 15%. In fact, vendors are finally beginning to embrace the entirety of the data ecosystem from end to end, and the ML ops market is slated to be over $4 billion US by 2025. So ML ops focuses on, at the minimum, the things that you see here, but also monitoring factors that were designed in during DevOps, as well as those that were not, will provide a baseline for your AI reliability. So let's review some of those monitors. Now, I won't go through all of these in detail, but these next two slides show some of the monitors that may be contributing to the rate of decay. They include topics from robustness, resilience, and trustworthiness that you see here. In typical reliability of our cars and refrigerators, these monitors would be known as stress tests, like vibration or mechanical. And these metrics help to mathematically predict how long the model will perform in the field. It is not an all-inclusive list. What you select is as important to monitor and highly dependent on what you have built in during model development or DevOps. The history of your model development, your history of your model implementation, and finally, the intended function of your model. Now, from simple statistical monitors here around concept drift and data decay that y'all are familiar with, to thoroughly understanding the drifts within your data and its pipelines. Models are living and learning entities that change, and retraining must happen routinely. And many of these monitors can help you identify the timing of that training. These are additional ML ops monitors to baseline your, to baseline your AI reliability. Adversarial ML, one of my favorites, it actually increases falses by poisoning and or evasion, and monitoring and understanding the root cause of the drift can protect your company as well as your customer from adversaries who mess with your models and associated features. bias, sampling, measurement, algorithmic, and finally prejudicial. We all have the inherent bias that we have to be careful of and test for. And what happens when societal norms shift? If your model is in the field, how do you monitor the shift of societal norms? Others, such as interpretability, which invokes UI and UX, user interface and user experience, anomalies, understanding drift in types, volumes, and periodicity, and of course, malicious attacks will add to your portfolio of ML ops monitoring. So what do you do with all this now that you have it? Well, let's consider then a theoretical curve for model decay. As decay occurs, there are several decay causes from the monitors that contribute to the metric. In this case, I've chosen the metric of accuracy. However, you may choose a different metric that reflects your model and business needs. These causes from the monitors are critical for understanding why the model is decaying. These causes can be combined, cumulative, or even single contributions to the decay over time. Now, in summary, consider DevOps and ML ops monitors of your business that are critical to the robustness, the resilience, and the trustworthiness that make up AI reliability. Consider those monitors listed on the 2 slides that I showed, prioritizing and editing to your specific business needs. Identify the units of the monitors and the output of those units and the amount of contribution to the decay, whether singly or in combination. Calculate a rate of decay based on an overall metric that your business recognizes as important, such as accuracy. Others might be false positives or even area under the curve. And finally, while I have stopped short of providing you the actual math for calculating mean time to decay or MTDD, consider system reliability calculations to get started, a merge of software as well as hardware reliability calculations. The most difficult part of AI reliability is honing in on the decay causes and that rate of decay. With implemented monitors within DevOps and ML Ops, you will be well on your way to predicting AI reliability for your company. Thank you very much, and please feel free to contact me if you have any questions. Thank you.